Redox reactions are named this way because they come from the terms reduction and oxidation. So if you squeeze those together, you get redox. When one occurs, the other occurs. So there's always oxidation and reduction are coming in as a pair. Okay, these are old terms, and so sometimes we're going to look at reactions and equations where maybe reduction or even oxidation doesn't really seem like it makes a lot of sense. But once you learn the more modern definitions, you see why those reactions are still called redox. So you can define oxidation reduction a number of different ways. The most technical way to define oxidation and reduction is based on electrons. And oxidation is the loss of electrons, whereas reduction is the gain of electrons. So again, that's the modern definition. If you look at that, you'd probably say that doesn't make any sense. Reduction is gaining. It's a little bit confusing, and I get that. In class, I'll talk about why maybe the term reduction was used in the first place. But you're just going to sort of have to live with the fact that oxidation is loss of electrons and reduction is gain of electrons. There are a couple of mnemonic devices to help you remember these things. So one of them is Leo goes Gur. That's my personal favorite. Leo like Leo the lion, and Gur like the sound the lion makes. And it stands for losing electrons oxidation and gaining electrons reduction. So that's one way to do it. Another one that people often use along the same lines is oil rig, which is oxidation is losing, reduction is gaining. So again, this has to do in terms of electrons, and these are a couple of little mnemonic devices that you can use. Okay. There are other definitions, though. As you may have guessed, sometimes the definitions have to do with oxygen. So for oxidation, gaining bonds to oxygen is one way to define oxidation. And let's try to just shrink down all of our text here. Hey, what just happened? There we go. And in terms of reduction, then, instead of gaining bonds to oxygen, losing bonds to oxygen. So sometimes we're going to have reactions that involve the element oxygen, and when something gets more oxygen attached to it, that would imply that it has been oxidized. And if oxygen is removed from something, that would imply that it had been reduced. You can also define these things in terms of hydrogen. So, sorry about that. I'm going to fix my text once and for all down to 20. There we go. Okay, so in terms of hydrogen, it's the opposite. Losing hydrogen, losing bonds to hydrogen, or just losing hydrogen is oxidation, and gaining hydrogen is reduction. Okay. Again, a little weird, doesn't have anything to do with the term oxidation or reduction in particular. But when we get to this last one, this thing called oxidation state, you're going to see why losing hydrogen is oxidation or gaining hydrogen is reduction. And you'll see why gaining oxygen is oxidation and losing bonds to oxygen is reduction. So we've got so far 3 different ways to think about what redox really is. Loss of electrons, gaining oxygen, losing hydrogen for oxidation. And they sort of, these different definitions apply in different scenarios. They apply better in certain reactions than others. And that's kind of a problem when you have a definition that doesn't always apply very well to a given type of reaction. And so to deal with that, the final type of definition that was coming up, that people came up with, had to do with these things called oxidation states. And oxidation states are always going to work for our redox reactions. So when you're trying to decide if something has been oxidized or reduced, the most surefire way to determine whether or not that has happened is to use oxidation states. And an increase in oxidation state is happens when something gets oxidized, and a decrease in oxidation state happens when something gets reduced. And so finally, reduction is sort of making sense here. There we go. We'll do it like that. It's a decrease in oxidation state. But again, it's better to see these things in practice. These are all different definitions and ways to think about what the terms oxidation and reduction really mean. The most technical one to know is the electron one, but the other ones do come up from time to time. So let's just look at some different reactions and see how these different definitions sometimes apply and sometimes don't. So here's a reaction, a net ionic equation for the reaction between zinc, metal, and copper 2+ ions. So if you put zinc into copper 2+ solution, the electrons will trade around and you'll end up with copper metal and zinc ions, zinc dissolved in the water. So this one, it's pretty easy to follow what has happened to the electrons. And here's why. I'm just going to copy it down twice, and I'm going to get rid of the copper from this one. So what I'm going to do is I'm just going to look at each element at a time. What I'm doing is something we're going to call half equations. I'm just going to look at one half of the equation at a time. Okay. So if I look at the zinc, you can see that on the left, the zinc is zinc metal, which means it has no charge. It's a neutral metal. On the right hand, though, it's zinc 2+. So we know already that if something goes from being neutral to being 2+, that means it lost 2 electrons. So on this side of the equation, I'm going to write in 2 electrons. Okay? And when I look at the copper, I see that it starts at 2+ and it ends up as normal solid copper metal. That means that its charge went from 2+ down to 0. And the only way that that could happen is if it gained 2 electrons. So this one fits our definition pretty well. Our first definition with the electrons, it's pretty easy to see. In the first half equation, we're looking at oxidation because I see that the zinc is turning into zinc 2+, and in order to do that, it has to lose 2 electrons. So the way I represent losing electrons is by showing them as a product, by showing them being given away on the product side, similar to how we would illustrate ionization energy. Down here, this is reduction, because in reduction, I'm gaining electrons. And the copper 2+ is gaining 2 electrons and turning into copper metal. So in this one, our original definition works out pretty well. The losing electrons is oxidation, gaining electrons is reduction. Leo goes Gur. Okay. Other ones work well in terms of like the oxygen or the hydrogen ones. So this reaction we're looking at here is called a combustion reaction, something burning in oxygen, making carbon dioxide and water. In this case, the something is methane. If you look at it at first, carbon has a lot of hydrogen on it. So sometimes you could say the carbon is fully reduced. So that has to do with that definition about hydrogen. It's got the most hydrogen on it that it can. That means that it's fully reduced down. Okay? And if you watch what happens in the reaction, the carbon goes from having lots of hydrogen on it to having no hydrogen on it in the product side. So carbon loses all its hydrogen and gains 4 bonds to oxygen. If you drew out the Lewis structure, there would be 4 carbon to oxygen bonds. So both of those things, gaining oxygen and losing hydrogen, equal oxidation. So we would say carbon has been oxidized. Okay. Now at the same time, you could talk about some of the other elements. We know that there must be reduction happening in here. So let's think about either what lost bonds to oxygen or what gained hydrogen. If you look at the right-hand side, all of the hydrogen is stuck to oxygen. So that means, if you look back here, yeah, at the beginning, the oxygen gas had no bonds to hydrogen, and afterwards, some of the oxygen is stuck to hydrogen. So it looks like oxygen was reduced. It gained bonds to hydrogen. You could also say, well, it lost some bonds to itself. It lost some bonds to oxygen. At first, oxygen is only bonded to oxygen. Afterwards, the oxygens are bound to hydrogen or to carbon. So they lost bonds to oxygen. So the bonds with the oxygen and the definitions with the oxygen and the hydrogen work fairly well for this example. The definition that would be tricky here is the one about electrons. And the reason why is that everything in this equation is covalently bonded. And we know that in molecules, electrons are shared. So it's a little bit tricky to talk about things losing and gaining electrons if they're always sharing them. It's like who owned the electrons to begin with and who owns them afterwards. That's a little bit problematic. So in this example, maybe the electron definition isn't great. We can use the hydrogen-oxygen definitions to try to figure out what gets oxidized and what gets reduced. In the first example, it was the opposite. The electron one was really easy to apply, or fairly easy to apply, but it would have been problematic to apply the oxygen or hydrogen definitions because there is no hydrogen or oxygen in that first example. It's not involved. So again, sometimes certain definitions will work better than others. And then finally, if you look at something like this that looks a bit crazy at the time being, it's really hard to apply either one easily. Maybe you could do the hydrogen or oxygen one, but you've got metals turning into ions, so you could look at electrons. But then you've got polyatomic ions that are covalently bonded and molecules that are covalently bonded. So it doesn't really fit neatly into a box. So it's best if we learn how to figure out oxidation states. So oxidation states are going to be a way that we can figure out where the electrons transfer from, which elements lose electrons and which electrons gain electrons. It's going to be a way to identify oxidation and reduction and which elements are getting oxidized and which are getting reduced. Okay, the rules for it, where it comes from, is you're assuming or pretending that every single bond acts ionic. And when things are ionic, that means you have ions. You don't have sharing of electrons. You have one element owning the electrons and the other one losing them. So the way the system works, if you actually draw out a Lewis structure, would be that the element with the greater electronegativity, we say it sort of owns both of the electrons in the covalent bond. And that's how you decide which elements have the electrons and which ones don't. If electronegativity is equal, then one electron goes to each of the covalently bonded atoms. If you compare the total number of electrons that we're now saying these elements own to the normal number of electrons, that's how you get an oxidation state. It's sort of like a pretend charge. Okay? So in oxidation states, the bonds are assumed to be 100% ionic, and we're going to erase that part about formal charge because that's an HL topic. Okay? The quick steps to determine oxidation state are as follows. So the quick steps for oxidation state are as follows. Number one, all elements in their normal state, so like their normal phase of matter, have an oxidation state of 0. That means that if you see copper solid, it's got an oxidation state of 0. If you see something like oxygen gas, normal oxygen gas, it has an oxidation state of 0. So any element in its normal form, oxidation state of 0. We know elements have no charge, and so that's why that's the rule. Monatomic ions have oxidation states that are the same as their charge. So in the other example, when you saw like copper 2+, if you were to see Cl- or H+, right? All of these ones, if the charge is just written in, you're looking at like a net ionic equation and you see an ions formula, then the oxidation states in these examples would be +2, -1, and +1 respectively. Okay, those are the oxidation states. It's important to point out that when you write a charge up above, like a superscript, you put the number first and then the sign. So 2+, you're also allowed just to put minus and plus if it's ones. When you write oxidation states out as numbers, the sign always comes first and then the number. Okay? And you wouldn't just say minus, you'd say -1 and +1. So some subtle differences about how you write them. Back to the rules. The oxidation states of a polyatomic ion or a molecule have to add up to the overall charge on the molecule. So if we're dealing with something like H2O, O, then oxidation states must add up to 0 because it's a molecule. It's water. It's a water molecule. There's no overall charge. If you were doing something like sulfate, and so you got SO4, and it's 2 minus, then oxidation states must add up to -2. Okay. And the last thing is what's really going to be helpful, which is that with some very rare exceptions, if you have oxygen in a compound bonded to other elements, its oxidation state is always -2 in those compounds, and hydrogen always has an oxidation state of +1 when it's bonded to other elements. Notice that I'm not including when it's an element. When you have like oxygen, or if you had hydrogen gas in their pure form, oxidation states are 0. Okay, so when I talk about these assumptions you get to make, that oxygen is always -2 and hydrogen is always +1, notice that's when bonded to other elements, not itself. Okay, so these are the main rules. The exceptions for oxygen and hydrogen are: for oxygen, when it's in its peroxide form. It's a polyatomic ion, O2, 2 minus. It also shows up in compounds like hydrogen peroxide. And so in those examples, oxygen has a -1 oxidation state. You can see in this one, if you have 2 oxygens in here and they add up to a 2 minus charge, then each one must be -1. And if you have 2 hydrogens, which are each +1, then how does this thing add up to 0? Because overall it looks like it doesn't have a charge. So you have 2 +1s. How does that balance out with those 2 oxygens? Well, each oxygen must be -1. And that way, overall, it's balanced and equals 0. The exception for hydrogen are the metal hydrides. These are some really rare and reactive compounds. Alkali metals always are going to be +1. Because they're that first group, they have very low electronegativity. So if you have Na, which is +1, then the only way for this thing to add up to 0 is if hydrogen is -1. So in both of the exceptions for oxygen and hydrogen, they end up with a -1 oxidation state. But the exceptions aren't that important. We more care about these rules, and the best way to ensure that we know them is to do a little practice. So on the next page, we've got all these different practice examples. Again, we're going to assume that oxygen is always -2, that hydrogen is always +1, and so usually we're just figuring out the oxidation state on the other element. So what I've given here is 11 examples in a row that all have to do with nitrogen. And just to show you how this works, I'll do the first couple, and then I'll leave the rest for you guys to try at home, and then we can talk about it in class. So in the first one, key is always start with the one that you know. So I've got oxygen. I know that oxygen has a -2 oxidation state, and there are 2 of it. So that equals -4. I've got 4 minuses here. Overall, there's no charge on this compound. That means that if they're going to add up to 0, with the overall charge, nitrogen must be +4 in this example. So I've got a +4 for nitrogen, and I've got -2 for oxygen. So notice that the oxidation state is the sort of pretend charge on one atom of each element. So for nitrogen here, it's +4, oxygen, it's -2. There are 2 oxygens. They add up to -4, but you would say the oxidation state on oxygen is -2. So for the first one, I'm going to erase the work now. Nitrogen is +4. Let's do another. In this case, we've got oxygen is -2. Okay. Again, there's no overall charge, so it has to add up to 0. And therefore, we must have 2 pluses. So we have 2 pluses. We also have 2 nitrogens to spread out those 2 pluses. So where does that come from? Well, if there's 2 nitrogens, what times 2 gives me 2? Well, I think we all know that's 1. So each nitrogen on this example is plus 1. Each oxygen is minus 2. So 2 times the plus 1 gives us plus 2 overall, and the 1 oxygen is minus 2, and that adds up to 0. So again, I'm going to erase the work and just leave the answer behind. I'm going to do one now that's a polyatomic ion. If we look over here at nitrate, in this case, the key thing to remember is that they have to add up to minus 1 because the charge on the nitrate ion is minus 1. Okay, so I've got 3 oxygens. I know that each oxygen is minus 2, and that means that adds up to minus 6. So if I'm going to add up to minus 1, that means the nitrogen must give me plus 5. Okay, so again, I've got, from the oxygen side of things, 3 oxygens. I know that they're each minus 2 because that's what we're allowed to assume. 3 times minus 2 gives me 6 minuses inside of this thing. They have to add up to minus 1, so there must be only 5 pluses. And since there's only 1 nitrogen, all 5 of those pluses must come from the nitrogen. So I would say that the oxidation state of nitrogen in nitrate is plus 5. Okay? So those are just some examples. How you figure out oxidation states, I'll leave the rest for you guys to practice. Give them a try. Try some of the ones down here. See if you get stumped at all. And that's really what we're going for. Once we are able to confidently apply oxidation states, it becomes really easy to see whether or not an element has been oxidized or it has been reduced. If you were to have a reaction where NO2 turned into N2O, you would very quickly see that going from plus 4 to plus 1 is a reduction because the oxidation state goes down for nitrogen. If you saw N2O turning into nitrate, you'd see that plus 1 was turning into plus 5, and that's an increase, and so you'd say nitrogen was oxidized. We're going to do more practice with applying them to reactions in class. For right now, make sure that you can apply the oxidation state rules. So if you got stumped in any of this stuff, make sure to stop the video, go back, check it out, re-listen to it, and by the time you get to class, I want you to know the definitions of oxidation and reduction, how sometimes they apply, sometimes they don't, and the rules for assigning oxidation states to elements in particles.